Okay, friends, we are back with example number 3, finding internal forces right here at point C. I'm going to try to work through this one a little bit quicker than some of the other ones, but we'll see how it goes. So when I want to find internal forces, I first have to see if I can cut it from the left or to the right, not have to find reactions, and it doesn't matter either way, I need reactions. So I'm going to draw a free body diagram overall, and I'm going to have an AY and a BY, and I know AX is 0 by observation. And then I have a load that looks something like this. Well, I don't really know what the equation is for the centroid of whatever this shape is. I'm sure there is one. I just like to go back and use kind of regular shapes. So I can break this up if we wanted to. I can draw this across, and I can see that I have a rectangle, and a rectangle will have a point load right through the centroid, and then I'm left with a triangle. And when I look at this, this whole height is 400. Let me erase that squiggle. But I've already accounted for the bottom 200 Newton per meter. So I'm going to have 400 minus 200. 200 newtons per meter is my new height of the triangle. Okay. And with a triangle, we know that we are 2/3 from the end with the right angle. So if I have 6 meters total and I march back, 1/3 times length, then I will get that this is right here 2 meters. This length is 4 meters. And my rectangular section has the centroid right in the middle. So we are going to have one right here and one right here. This is 2 meters. 4 meters, 3 meters, 3 meters. Okay, I just like to go ahead and mark everything that I can. So now I need to find the values of these point loads. It's just the area under the curve. So if I look at my rectangle, area is base times height. I have 6 times 200, so I get 1200 newtons. Area of a triangle is 1/2 base times height, so I have 1/2 times base times height, doink, doink, 100 newtons. That's not correct. It would be 100 times 6, which is 600 newtons. I need my friends in class to tell me where I've screwed up in my math. Oh, and I need people to tell me that you can't see the screen. Move stuff around a little bit. Okay, there we go. I think I can do this. Is that more straight for you all? I kind of write sideways. Okay, so now I am going to sum moments about B equals 0. I'm going to put my finger over here at B, try not to cover up everything, and I'm going to have a negative AY times 6 meters plus 1200 newtons times 3 meters plus 600 newtons times 2 meters equals 0. And the beauty of labeling everything is when it comes down to writing equations, I don't have to think about what I'm doing. And we get AY is 800 newtons up. So if I were to sum forces in the y direction, I would find that we have 800, we'd have 1,000 newtons up. So I'm going to go back and kind of draw those on my free body diagram over here. Okay, so now I want to know at point C exactly what my internal forces are. When I'm looking at point C, I can approach this from the left, or I can approach this from the right. Okay. This is kind of a mess. I'd have to use both a rectangle and a triangle, but then I'd have to like make another rectangle because that's a mess. So I think I like this triangle and rectangle. So I draw a new free body diagram of my section A to C, and I'm going to draw everything that I can see to the left, and we are going to use positive beam notation in order to find those internal forces. I'm going to start at the left. I have 800 newtons, and then I can see I have something that looks like this. 3 meters. I know that the height of this rectangle is 200 newtons per meter, okay? And I also know that the centroid is going to be right there at 1.5. We're going to erase that. We know that this whole length is 3 meters. So I know that this length is 1.5 meters. And this length has to be 1.5 meters. Our triangle is going to have the centroid 1/3 back from the right angle here in the larger part of the area. So this is going to be 1 meter. And if I come this way, it's 2 meters. So now I've got my forces labeled in terms of where they're going to be located. Now I just need to find the amount of those point loads. And again, it's just area under the curve. So I have a rectangle. So I'm going to have 200 times 3, which is 600. And I have the area of a triangle, 1/2 base times height. So I have 1/2 times 3. Okay, height. Well, I can't really use the 400. I can't even really use the 200 of the actual height because we're only halfway back. So I can use similar triangles that we have 6 is to 200 as 3 is to blank. I can look at this because it's in the middle and I know that the slope right here is 100 newtons per meter. So now when we're finding that area, it's 1/2 base times height. And I'm going to get a magic number. Let's see what that number is. If I did my math right, 0.5, enter 3 times 100 times, and I get 150. Sorry, it's kind of all getting messy here. Now I can sum forces X, and my normal force is 0. I can sum forces Y, and I get 800 minus 600 minus 150 minus shear. Remember, it's positive behavior, but it's a negative direction when we're doing our rules of equilibrium. So I'm going to get V equals 800 minus 600 is 200 minus 150 is 50 newtons. Okay? And is that right? 800 minus 600. I should use my calculator. 800, 600 minus 150 minus, and I get 50. So we have positive shear, which means that the positive behavior we assumed is correct. Now we're going to sum moments about point C. I'm going to use right-hand rule. I don't know why I drew it twice. Here we go. Negative 800 newtons times 3 meters plus 600 times 1.5 meters plus 150 times 1 meter plus moment equals 0. Okay, positive behavior, it also happens to be positive because of right-hand rule with statics. So when I multiply this out, I'm going to get 800, change signs 3 times, 600, enter 1.5 times, 150, enter 1 time. So we're going to go plus, plus. So I have negative 1350 plus m equals 0. So my moment is a positive 1350 Newton meters. Make sure you have your units. And if we think back, positive moment means we have deformation, or we have compression at the top, tension at the bottom of the beam. I want you to go back to look at your overall picture here. If I'm pinned and on a roller and we are all standing on this beam, we can see very clearly it's going to make a smiley face curvature. That's indicative of positive internal moment. So even if our math isn't right, we at least got the correct sign convention for our moment. Okay? If you have any questions, make sure you're visiting with the TAs. And remember, you guys can pause these videos as we're going through so that you can work them out ahead of me and then check your answers. Okay, I'll be working on the shear moment diagram for this using equations next.